Now that you kind of are getting the hang of drawing the Lewis structures for covalent compounds, we're going to look at an application of drawing those structures, and it is called the molecular geometry, and that just means the shape that the molecule or covalent compound makes when it forms its bonds. And the basis for the shape that is made is based on the valence shell electron pair repulsion theory. And sometimes we call that VSEPR, VSEPR, the VSEPR theory. And the idea behind this theory is that electrons will repel each other, and electrons, remember, are located either in shared pairs or in lone pairs. And we call both shared and lone pairs electron regions, and those regions will repel one another. When our electrons are shared pairs, they're connecting atoms, so we will call those just kind of our shared bonding regions. And then anywhere that there are lone pairs, those are non-bonding regions. When we're looking at the shape of a covalent compound or molecule, we will be observing specifically the bonding and non-bonding regions around the central atom of our compound. So in on this page, all of the central atoms are drawn in red, and then you'll see kind of surrounding connecting atoms are green, and the bonds, of course, are lines. So we're going to fill in this chart just noting how many bonding regions and non-bonding regions are around that red central atom for each shape, because our electrons will repel one another within the bond, causing it to form kind of a bond angle where they are as far away from each other as possible. They're repelling one another to create a specific shape. When we have two electron regions, and really the only option here is going to be that they're both shared pairs, so we would say that this is two bonding regions. So I'm going to put 2 with a B just to show we have 2 bonding regions around our red, and we have 0 non-bonding regions. Remember, again, bonding regions that we're describing the shared pairs around the central atom, and non-bonding regions are lone pairs around the central atom. Linear is going to end up having a 180-degree bond angle with 2 bonding regions and 0 non-bonding regions, giving us the shape linear. Looks like a line. If we enter into 3 electron regions, now we have options for there to be bonding or non-bonding regions. So let's continue with all of them as bonding first. So this would be 3 bonding regions and 0 non-bonding regions. If that is the case, our shape is trigonal planar. And that just kind of looks like a peace sign, if you will. If I drew a circle around this, it would look like a peace sign or a circle cut into thirds. Trigonal planar, this will be the way that the electrons can most efficiently repel one another within the shape of the molecule. If I have one of those electron regions as a lone pair or non-bonding region, the overall shape holds, but I only see the parts that are connected with atoms. So instead of it being trigonal planar, this one would be considered bent, with 2 bonding regions and 1 non-bonding region. A total of 3 electron regions, which is why it holds this overall shape. However, one of them is a lone pair, and the other 2 give us the bent shape when we have 1 non-bonding region. When we go into 4 electron regions, we tend to think of kind of like an X or a cross to be 90 degrees apart from one another. But because this is in 3 dimensions, molecules are 3-dimensional, we actually have a larger bond angle or a greater repulsion that the electrons can make than 90 degrees. And that is through the shape that kind of looks like a tripod. If you think of this, this one's kind of like going out of the page, and these are kind of coming out of the page. If you can kind of visualize that in 3 dimensions, then you can see this is like the bottom of the tripod and then the top of the tripod, and that would be how we would see this shape for 4. And its bond angle ends up being a little bit larger than 90 degrees. It's actually 109.5, kind of particular there, but that ends up being a larger bond angle to repel the electrons a little bit better. So if we have all 4 bonding regions, then this would hold and maintain that shape of tetrahedral with no lone pairs. Now, if one of them is a lone pair, just think of kind of losing that top of the tripod, and now we just have the tripod legs. So the tripod legs here at the bottom, this one's called trigonal pyramidal, or sometimes it's called trigonal pyramid. Both can be used kind of interchangeably. It's just those 3 bottom legs of the tripod, kind of looks like a pyramid. This would be 3 bonding regions, 1 non-bonding region. So overall, the electron regions hold the shape of tetrahedral, but we only see the 3 that are bonding in our compound. And lastly, if we have 2 bonding and 2 non-bonding, now we are back to kind of that V bent shape like we saw in the previous example where we had a bent with 2 bonding and 1 non-bonding. When we get into 5 and 6 electron regions, it gets a little bit more fuzzy to visualize, but I'm going to do my best to help you kind of understand what this looks like. So if you think about a ballerina, if you will, think of this as like the head and then the 2 arms and then their little feet sticking out, one in front and one behind, kind of like a star in 3 dimensions. This would be our trigonal bipyramidal when we have 5 bonding regions and 0 non-bonding regions. Then seesaw is if you think about like a little seesaw that kids play on at the park. This would be kind of the 2 legs at the bottom, and then the actual part of the teeter-totter that kind of goes up and down, if that helps you visualize. Kind of a nicer way than saying a decapitated ballerina, but that is kind of what we're seeing here, where we have 4 bonding regions and 1 non-bonding region. Seesaw. T-shape is our next one. T-shape, if you put your feet together and put your arms out, there's T-shape with 3 bonding and 2 non-bonding regions. And then lastly, if we take away kind of those 3 middle parts and just kind of have your arms out, so no head, no legs. Now we're back to linear. This would be 2 bonding regions and 3 non-bonding regions, all kind of holding that shape of our trigonal bipyramid. But as we add lone pairs, we do not actually get to see those bonds because there's no atom attached to them. And so, although the electrons will repel and kind of hold that position, we'll see these other shapes of the molecule start to emerge. And then the last one is 6 electron regions, and what you'll see is kind of like an X, kind of a flat X with something coming out the top and out the bottom. So you think of this kind of, let's see, going into the page, coming out of the page, coming out of the page, and going into the page. If you can kind of visualize that in 3 dimensions, you've got like an X there, and then you've got a top and a bottom. So this shape is called octahedral. 6 bonding, 0 non-bonding. Square pyramid, if we take one off, now you've kind of got 4 legs on the bottom with 1 coming out the top. So this would be square pyramid. Think of it like an X with 1 coming out. 5 bonding, one non-bonding. Okay. Then square planar, now there's just the X, flat X. It's kind of what people usually think tetrahedral is, but that's actually square planar, just an X by itself. T-shape, kind of like we saw previously, this would be 3 bonding and 3 non-bonding. And then lastly, linear. Two bonding, 4 non-bonding. Now you do not have to have these shapes memorized. You'll be able to see and use this reference sheet on the test. You will just need to identify in a Lewis structure how many bonding and non-bonding regions there are and then match to the sheet. So let's do some practice problems with this. What is the shape of the molecule? So in number 1 we have silicone, that is our central atom. So always identify your central atom, kind of like that red circle in the middle, and then start looking for bonding and non-bonding regions. Now in these problems you're going to want to make sure you're not looking at any of the lone pairs on our outer guys. All we care about is what's directly affecting silicone because it is the central atom. So in this case we have 1, 2, 3, 4 bonding regions and 0 non-bonding regions because there are no lone pairs on the central atom. If we look back at our chart, 4 bonding and 0 non-bonding is the tetrahedral shape. Number 2, germanium is our central atom. We have bonds here and bonds here. Each of these double bonds counts as just one bonding region, not as 2, even though there's double bond. It's just one bonding region, one location where there are electrons. So we have 2 bonding regions, 0 non-bonding regions, and then we check our chart. 2 and 0 is linear shape. Let's do one more together here. Central atom is phosphorus. We have 1, 2, 3 shared pairs and 1 lone pair on our central atom. So we have 3 bonding and 1 non-bonding region. That would be trigonal pyramid. Use the chart to complete this page.